Hi everyone, this is my video number 17, and I'll talk on procedure of how to reduce the non-homogeneous Volterra integral equation of the second kind into differential equation and find its solution, and as well as reduction of Volterra integral equation of the first kind into non-homogeneous Volterra integral equation of the second kind. Okay? So the main ingredient here is that the use of a Leibniz rule. Okay, so first let's look at the how can we reduce the reduction of non-homogeneous. I just write like this, right? Non-homogeneous Volterra integral equation of the second kind into differential equation, and its solution. So I hope you can read those things. Reduction of non-homogeneous Volterra integral equation of second kind into differential equation. Okay, so the first step that we need to do is of course, the given integral equation we need to write into Volterra integral equation, non-homogeneous Volterra integral equation. So first thing is write the given integral equation into the non-homogeneous Volterra integral equation. So we have ux equal to fx plus lambda 0 to x k xt ut dt. Okay, the second thing is that we use Leibniz rule, differentiate. Let's call this equation 1. Differentiate 1 with respect to x. Here we use Leibniz rule. So what is the Leibniz rule? Let me write down here. The Leibniz rule is given as that we differentiate under the integral sign from some limit ax to bx a function of f xt dt. This is equal to, we evaluate those function at upper limit, so we have x fx bx, then we differentiate those upper limit, so d dx bx, okay, minus, then we evaluate at the lower limit f x ax, we differentiate those lower limit ax plus integrate ax to bx. We have k or del, in this case our f, so del x f of xt dt. Okay, so this is the Leibniz rule. And number 3, so 1, 2, 3, number 3, we just solve the obtain differential equation. Solve the obtain differential equation. So this is the way how do we reduce the non-homogeneous Volterra integral equation of the second kind into the differential equation. Now I won't give, I don't have any example for this because to do this process from 1 to 2, this is not difficult. But at the number 3 here, this is involve the integral equation, so I don't want to touch that much in this lecture. Now the second problem is that the reduction of Volterra integral equation of the first kind into reduction of Volterra integral equation of the first kind into non-homogeneous Volterra integral equation of the second kind. Okay, so again we use almost similar approach here. First thing we need to write in terms of the given integral equation as a Volterra integral equation of the first kind. What is Volterra integral equation of the first kind? So we have basically this is given as fx is equal to 0 to x k xt ut dt. So this is the Volterra integral equation of the first kind, and the solution is, or the existence of the solution, the existence of the solution is guaranteed by, so the existence of the continuous solution, continuous solution. So the condition we need here is f0 must be 0. The existence, to guarantee the existence of the continuous solution of the Volterra integral equation, is that f0 is equal to 0. Now let's do this. Now this is the given Volterra integral equation of the first kind. Okay, so if we differentiate this using the Leibniz rule or Leibniz formula, so what we have, so this is our f here. Okay, this is our f. If I consider that all those things, so we have f. So we have f. So if we differentiate, let's call this 1. Okay, so we differentiate 1, that this equation using a Leibniz rule. So what we have, so all those things is our f, so that gives us k x, our t is x, u of x, and d dx limit is x minus k x 0 u 0, then d dx 0 plus, we have this part here, integrate from 0 to x del we have del x k xt ut dt. Okay, that's on the left side. On the right side we have, sorry, that's the right side. Then the left side we have, I put it right hand side, so f prime x. So what we have here, this is 0 because we differentiate with respect to 0 here. That gives you 1. Alright, so what left is that we have kxx ux, that's plus integrate 0 to x del x k xt ut dt, this is f prime x. Now from here, the we can write or we cannot write into the Volterra integral equation of the second kind very much depend on the kernel, the evaluation of kernel at x. So if this is 0 or if it's not 0, so if kxx is different than 0, so what we can write is that you can divide through this, and I just bring out that term to the right side. So you can just divide by kxx. What left is you can write this thing as a ux is equal to f prime x over k xx. Bring that side. This is integrate 0 to x. I can write this as a kx. Alright, means partial derivative with respect to x. So that give you kx xt ut dt. This is divided by k xx. Okay, and from here, this is nothing except the Volterra integral equation of the second kind. So this is the Volterra integral equation of the second kind, where in this case this is your f. You compare with the Volterra integration of the second kind. Also, we have ux is equal to fx plus lambda 0 to x or a to x. I can say the kxt ut. This is the general form of the Volterra integral equation of the second kind, where if you compare with this, you can see this is our fx. Compare with that, this is our fx. Lambda is -1, your a is 0, x is x, and your k is kx xt over k xx. So that's your k. So and we have ut. So basically this is the integral equation, Volterra integral equation of the second kind. So what we have done now, we have reduced the Volterra integral equation that of the first kind to the Volterra integral equation, non-homogeneous Volterra integral equation of the second kind. That for the case of kxx is 0. Yeah, kxx is 0. But if this is not 0, what happened? You can see from here, if it's not 0, so we still have that form, alright, because this is not 0. Then you need to differentiate again. Okay, you need to differentiate again, because this is still the Volterra integral equation of the first kind. Yeah, still integral equation of the first kind. Then you need to do the process to integrate again. So what you got, if you differentiate those, if kxx is 0, so let me give a name. That's kxx. So I have this. So let's call this equation here, this is equation number 2, say. Okay, so we differentiate this, differentiate 2, and again rearrange. Yeah, rearrange. I ask you to rearrange. So what we have using Leibniz rule, so what we have is that kx xx ux plus integrate kx xt ut dt, that's equal to f double prime x. And again the process, if kxx xx is 0, you know, similar process as before, then you can write this ux in terms of non-homogeneous Volterra integral equation of the second kind. If kxx is 0, what you have there is 0. Okay, so what left is only that. This is the Volterra integral equation of the first kind. Then you need to do the process again and again. Okay, if you do this process until you get you differentiate x as much as n minus 1 times xx, that is different than 0. So what we have, basically, you can write those equation as kx. Okay, just keep all those process in between. We have kxx ux plus integrate 0 to x del xn n times. We have k xt ut. Okay, so we differentiate respect to x n time, so dt, this is equal to f and x. Okay, and of course, as long as that condition satisfied, you can always write ux. You can always write ux as f and x over kx n minus 1 xx minus integrate 0 to x kx n x t ut dt over k x n minus 1 xx. Okay, which is the non-homogeneous Volterra integral equation of the second kind. So let's see example of how to deal with the equation of the Volterra of the first kind. You remember that Volterra integral equation, to solve Volterra integral equation of the first kind, you need to identify those things. Need to reduce to the Volterra integral equation of the second kind. From there, we have the solution in terms of resolvent kernel. If you remember that we have the solution into the resolvent kernel. Now, in order to obtain the resolvent kernel, you need to use iterated kernel to obtain the general form of the iterated kernel. And then you can just find the resolvent kernel and then substitute into the general form of the solution. Then you can solve the problem. Okay, now, so that's basically the recap what I going to do. All right. Okay, let me write those things. We are going to solve the integral equation, the Volterra integral equation of the second kind, fx plus lambda, let's say from sum a to x, all right, kxt ut dt. Yeah, the solution can be written as solution can be written as so we have ux is equal to fx plus lambda integrate from a to x r xt lambda ft dt, where r here is the resolvent kernel. The resolvent kernel can be written as a summation of m from 1 to infinity lambda m minus 1 k m xt. Okay, and this k can be obtained using iterated kernel. Okay, so that's the process to solve the Volterra integral equation of the second kind, the non-homogeneous Volterra integral equation. Yeah, we write the solution can be written as that. where R is the resolvent kernel. The resolvent kernel can be obtained from that series, and the K can be found from the iterated kernel. Now let's say we want to solve example. We have just solve lambda integrate 0 to x e x minus t ut dt that equal to sine x. Yeah, this is the example. If you compare with the general form, we have what? The general form we have integrate from a to x, we have k xt ut dt, this is equal to fx. This is the general form for the first kind Volterra integral equation. Now, to ensure the existence of the continuous solution, to ensure the existence of the continuous solution, so what we need to check is that you check f0. Yeah, in this case our f is sine, so f0, so sine 0 is 0, so that give you f0 equal to 0. So this will guarantee the existence, existence of continuous solution. Okay, so that condition guarantee the existence of the continuous solution. Now let's do how to solve this this example. Let me write those. We have the equation given as lambda integrate from 0 to x e x minus t ut dt. This is equal to sine x. Okay, then if you use the differentiate this, let's call this 1. Okay, we differentiate 1. We use again the Leibniz rule. Remember the Leibniz rule. So we have we differentiate, we evaluate those at upper limit. So we have e x minus x, e x minus x, ux d dx, x minus, we differentiate lower limits. So we have e x minus 0 u0 d dx of 0 plus, we integrate from 0 to x, and then we differentiate del x e x minus t ut dt, and on the right side we differentiate respect to x, that give you cos x. Okay, if you rearrange this, of course this one is 0, that you have 1, that you have 1, so what you have is ux is equal to cos x minus this thing, yeah, minus integrate 0 to x, you differentiate this, you got e x minus t ut dt, and this is actually our f prime x. Now you can name it as let's say capital F of x. Just give a name. The reason why, because we need those things in order to find the general terms. And also your lambda in this case equal to minus 1. Your kernel is e x minus t. Then we use the iterated kernel, because here this term here, this is the Volterra, the non-homogeneous Volterra integral equation of the second kind. Yeah. Right. So now we are going to solve this. Now, in order to solve this, we need to write this, or the solution can be obtained in terms of resolvent kernel. To find the resolvent kernel, we need to find the m term of the kernel, the iterated kernel. Then you can find the resolvent kernel. So let's do those. So by the iterated kernel, we have K1. We have K1 xt. This is K xt. Alright. This is equal to, we have E x minus t. So we can find K2 xt. This is, we integrate from t to x, K xz, K1 zt dz. Okay, if we do this, what we have, t to x, K xz is x e x minus z, kzt is e z minus t dz. So what we have here, this is x e x minus t. Okay, so you can have, this is x minus t e x minus t. That's K1. Then you can find K3 using the same process there. The K3 is given as t x k xz K2 zt dz. So if you do this, you're going to have x minus t squared over 2 factorial e x minus t. And hence you can find what is K mx, which is given as, you can find those, make it the gender terms. So we have x minus t m minus 1 over m minus 1 factorial e x minus t. Okay, so having obtained the m terms of the kernel, iterated kernel, we can write the resolvent kernel. So therefore, we have the resolvent kernel can be written as x t lambda. This is a summation of lambda m minus 1, m from 1 to infinity. We have k m xt. Alright, so if you write this thing, you're going to have m equal to 1 to infinity. Our lambda is minus 1 here. Your lambda is minus 1, so we have minus 1 m minus 1. Our km is given here, so we have x minus t m minus 1 over m minus 1 factorial e x minus t. Okay, so you can arrange that. So what you have, okay, so we have that you can factor out. Okay, so we have e x minus t, and then for the first term m equal to 1, so you got, this is give you 1, this is give you 1, that's give you 1, so you have 1. When m equal to 2, you have minus 1, so we are negative here, and then that one is already taken out, 2, so we have x minus t over 1 factorial plus you have x minus t 2 over 2 factorial, and so on, plus minus and plus minus, plus minus, and this one minus, and so on. So what we have here is that e x minus t, this is the series for e x minus t. We have plus minus, so we have negative x minus t. So that give you 1. Okay, so therefore the required solution, so therefore our solution is given as ux is, our fx is, the general solution. I wrote somewhere, where is it? I wrote the general solution. Here. This is the general solution I have written here. So we need to write that. So our lambda is -1, our f is cos x. So I just put it down there. So the general solution is given as, so we have our f is where is it? Cos x. Cos x. Cos x. Lambda is -1. We integrate from 0 to x, and this is our resolvent, which is 1. Okay, and our f t, which is cos t dt. So solve this, you're going to have, let me write here, this is cos x minus sine x. Okay, so that's the solution. Alright, let me give you one more example before we end up this video. Again, we're going to solve the integral equation, Volterra integral equation of the second kind. So we have 0 to x, ax minus t ut dt equal to fx, and given that f0 is equal to 0. As I mentioned earlier, that condition will guarantee the existence of the continuous solution. Now, solving that equation, again, the process is we need to reduce to the non-homogeneous Volterra integral equation of the second kind. Then we need to find the iterated kernel. We need to find the m term of the iterated kernel. Then we need to find the resolvent kernel. Then the solution can be written appropriately in terms of resolvent kernel. Okay, so let's do it. Okay, if you differentiate this, okay, remember this is a to the x minus t. So if you differentiate that, you'll got the term of log. So let me give this name, equation number 1. It's easy for me to recall. So we differentiate 1, that give us, remember that we use the Leibniz rule. Okay, so we have a x minus x ux d dx x minus a x minus 0 u0 d dx 0 plus integrate 0 to x, here d dx a x minus t ut dt. Then we have right side f prime x. So obviously this is 0, this is 1, this is 1. So what you have is ux. So you can write this as a ux. You can write that as ux equal to, I can bring this to the other side. So we have f prime x minus, differentiate this, you have log of a as a base, log a. So you have log a, base you can put base e, ln, and then integrate 0 to x. ax minus t ut dt. Okay, now you have the Volterra integral equation, non-homogeneous Volterra integral equation of the second kind. So you compare with the general form of the Volterra integral equation, non-homogeneous Volterra integral equation. So we have fx is our f prime x. Our lambda is actually minus log a. Our k xt is ax minus t. Okay, so from there you can find what is k1. From this k, you need to find what is k1 xt. This is equal to a xt, which is a x minus t. K2 xt, we integrate from t to x, k x z, k1 zt dz. Okay, so integrate this t to x, k1 kxz is a x minus z, k1 zt is a z minus t dz. Okay, so if you integrate this, you got what? Okay, z minus t, x minus t. So you have x minus t, you have a x minus t. So for k2, if you write k3 xt, you can do the same. T to x, kxt, k2 x, so xz here, zt dz. Okay, if you do this, you'll got x minus 2 squared over 2 factorial ax minus t, and hence you can find what is km xt is given as x minus t m minus 1 over m minus 1 factorial a x minus t, and hence you can write the resolvent kernel. Therefore, the resolvent kernel k rx t lambda, which is given as or written as m1 to infinity. So we have lambda m minus 1 km xt okay, so you just write this thing. We have k1 xt plus lambda k2 xt plus lambda squared k3 xt and plus on plus lambda n minus 1 m km xt and so on. Okay, and if you do this, you got this is equal to 1, and therefore the solution is given as ux is equal to f prime x minus fx log a. So that's the final solution. Okay, so that's the example. So basically that's the end of our video today. So let me recap what I have explained. So we try to solve the Volterra integral equation of the first kind. Yeah. Oh. We solve the Volterra integral equation of the first kind So what we do is that the solution process that we need to reduce those Volterra integrate equation of the first kind into non-homogeneous Volterra integrate equation of the second kind. Now, once we obtain the non-homogeneous Volterra integrate equation of the second kind, you can solve this using either we reduce into differential equation and find the solution as normal in differential equation, or you can use the iterated kernel, write in terms of resolvent kernel, then you can find the solution, or you can use the approximate solution as well. The method that we have learned in solving the Volterra integrate equation, non-homogeneous Volterra integrate equation of the second kind. So with that, I thank you. We stop here for the video. Bye.